is actually two more on this slide. The one that's described there is actually the fourth one that I wanted to do. So let me renumber these. I'm actually going to put that back and say that that is 4. There we go. So that's 4. And we're going to do this one sort of over here on the right-hand side. And before that, I want to do number 3, which is also going to use a cylinder or a box. Well, for this one, a cylinder only will work, it turns out. And let me tell you what this problem looks like. It is a very long, think so long it might as well be infinite, okay? A very long, straight wire with a positive charge density. Positive charge density, and we'll call that lambda. Long straight wire with a positive charge density lambda. Also, if it gets a little too chilly on this side of the room, or this starts just waving so much it makes you a little ill, let me know and I'll close that window. I already noticed it was billowing quite a bit, so if that drives you a little insane, just say the word. A cylinder, we're going to have a very long straight wire with positive charge density lambda. So, what I mean by that is literally we're just going to say there is a wire that basically has no real thickness to it that we can discern. We're going to say that it's really, really thin and small, such that when I think about the charges that are lined up, it's almost like they're all in a row, like they're in one dimension. So you might think of these charges like this. Here we go. Positive charges all along this wire. So we're not going to be able to go inside the wire like we did with those previous examples where we like had an inside answer and an outside answer. This is so narrow and thin that we're just going to try to find something about the electric field outside. So first of all, if I just drop positive charge anywhere, let's say here to begin with, which direction will it be pushed? It's going to try to get away from all those positive charges. If I put it in the front, which way is it going to be pushed? Like straight away from all those positive charges. If I put it behind, it would get pushed away from all the positive charges. If I put a positive charge on top, it gets pushed up, right? So you could imagine an electric field that sort of looks like this in all directions, radially around this wire. Electric field everywhere. So in other words, if I were looking at the wire sort of end on, right, and I could just see like the end with one of my positive charges, we're imagining that there's an electric field that points in all directions out from the wire on all sides. So this is an end view of the wire. And I should label that electric field too. There we go, electric field, electric field. So we're going to try to find the value of, or rather an equation or formula or an expression that tells us the electric field some distance away from the wire on any side. We're going to go to some distance r away from the wire and find the electric field. So to do that, I'm going to set up a Gaussian surface that is a cylinder. And this is where things artistically get a little difficult. But hopefully you can sort of get the idea. Okay? I'm putting a cylinder that's imaginary around the wire. And you can imagine the wire passing sort of straight through the center of the cylinder. Again, if we look at it end on, essentially it's just a circle if we're looking at it from the end. Okay? Can everybody at least partially understand what I've drawn? Sort of. Okay, we got it. So let's see. What was I using previously? So we're going to say that this has a radius r. We'll use a capital R for that. And if you think about it, my electric field is passing through this imaginary surface, this Gaussian surface, this cylinder. Some of it is passing through the walls of the cylinder, right? The rounded part on the side of the cylinder. Some of it may or may not be coming out the ends of the cylinder. There's 3 different surface areas on a cylinder. Unlike a sphere, just one big surface area, here I've got 2 end caps that are circles, and then I've got this rectangle that wraps around the side of the cylinder. We're going to look at the flux that passes through all parts of those, okay? So in other words, when we write out Gauss's law, so let's start with just our overall equation. It's E dot dA is equal to Q enclosed over epsilon naught. We are essentially going to have 3 parts on the left-hand side because I've got 3 different areas to deal with, okay? So once you see what it looks like, I'm going to do a lot of work to show you how simple it actually is. So the next time you do something like this, you might not need to draw all this much. So I'm going to say E dot dA for the side of the cylinder plus E dot dA for one end of the cylinder plus E dot dA for the other end of the cylinder. I don't know what happened to that last cylinder. It just kind of turned into I got kind of lost in the middle there. Did you get the idea? That's the left-hand side of the equation simply because my cylinder has 3 different surfaces that I need to consider how much electric field is passing through, okay? On the right-hand side, we still have Q enclosed over epsilon naught. So let's talk about this circle on the one end of the cylinder. How much electric field is passing through that end? None. Yeah, none is the answer. I'm going to pretend all of a sudden that this is the cylinder. I'm hoping the lid is on there okay, right? You can imagine if the electric field is sort of going past the end, it's not actually going through that circle. Much like when we talked about if I put the iPad like this and the electric field is going this way, it just sort of flows past it, but doesn't actually pass through that surface. So there is no flux passing through that end. No flux. I don't know why I keep writing the wrong letters. And you might quickly arrive at the idea that there's none passing through the other end either. So it's also 0. The key that I want to point out is that you have to think about all of the surface. Here it's broken into 3 different parts. So any flux that I have passes through this side wall of the cylinder. Okay? So let's see. Let's bring this down. And we're going to say that the electric field will be constant a given distance from that. So I'm going to pull that out of the integral. And this closed surface integral of dA is just going to be the surface area of the side of the cylinder. We'll put a big equals and put Q enclosed over epsilon naught. We're getting close to an answer here, believe it or not. What's the equation for the surface area of the side of the cylinder? It's close. That's one of the dimensions. It's 2 pi r times the length, right? If you unwrap the cylinder, it's a rectangle. And the length of one side is the circumference of the circle. And then I have the length of the rectangle as well, or the length of the cylinder. So this side is going to be E times 2 pi r L. That's the surface area of the side of the cylinder. The circumference is one dimension, the length of the cylinder is the other dimension. So let's go ahead and write in L here for the length of the cylinder. There we go. Now remember, going back up here to this positive charge density, this linear charge density is Q over L. Okay, linear charge density is represented by Q over L, which would also be Q enclosed over L enclosed. And you can see that I can rearrange that and substitute in for Q enclosed, right? So this Q enclosed, whoops, we don't want to put that up there, is going to become lambda times L enclosed. And let's keep the epsilon naught in the denominator. Now notice, this L that's on the left-hand side, that's the length of my Gaussian surface. This L on the right side, L enclosed, well, the enclosed length is also the length of the Gaussian surface. Those are the same thing. So let's cancel them out. Okay, we describe them a little differently, but they're describing the exact same length. Which means that we're basically done. We can rearrange that for E, and now we have lambda over 2 pi epsilon naught r. If you know the charge density in your line of charge and you go to a certain distance, you can find the value of the electric field at that distance away from that charge distribution. I think, on a whole, that was a little easier than some of the other ones we did last week. Maybe. Maybe. Just say yes. Maybe. Okay. We're going to do one more. But let me pause and see if anyone has questions about this one. Is there anything up there that's just bothering you a little bit? You're thinking, the whole screen bothers me. I understand. It's okay. We'll get there. Have you started your homework? This is where I look out and I see people that are doing this. I can look anywhere in front of the classroom. I get that. Also, checking WebAssign just before I came in here, I think 59 of you are registered out of the 80 or so that are in the class. So I'm very much aware that, yes, 20 of you haven't even logged on and signed up and accessed it yet. Do it today. Got that? Otherwise, I will hunt you down and put your fingers on the keyboard and say, do things there. Okay, because that's about as much as I can threaten, really. Okay? So do that today. There have been some complaints of access codes not working. And if you bought the book previously, you're supposed to still have access. If you bought it last semester for $220. So if anything's not working right, I need to know as soon as possible so we can get all that resolved. Okay? So make sure you try and let me know if you have problems. And then, as soon as you get it resolved, work on the homework. Go buy a burrito, sit down, work on the homework. Okay? Actually buy 4 burritos, 2 for you, 2 for a friend, and work together. Okay? Sound good? 6 burritos is better, maybe? 3 for you, 3 for a friend? I don't know. Maybe an infinite supply of burritos until the homework is done. Just keep the burritos coming. Whatever it takes. Just get started on the homework, all right? I'm going to insert a slide here because it turns out that took more room than I thought it was going to. So let's see, add a page. And it's going to come out the wrong orientation, but it'll still get the job done for us. And we're going to do one more problem, and this will be the fastest one of them all. It was described on the previous page, but I'll write it here again. This is an infinite insulating plane of charge. We will say that it has surface charge density sigma for that. Surface charge density positive sigma. So, oh boy, here we go with the artistic troubles once again. Okay, plane of charge. Imagine an iPad, okay? Infinitely small perhaps, such that instead of just having a line of charge, it's like a bunch of lines of charge all sort of lined up. So if we wanted to kind of like try to draw it with a little bit of perspective, right? It's just like a bunch of charge that's all evenly distributed on this plane. And we're going to say that it has essentially no thickness. I could look at it from either side and be like, look, plane of charge. And I could look at it from the other side and be like, look, plane of charge. But if I look at it from the side, there's almost nothing there, okay? So that's kind of a perspective view. It might be a little easier just to sort of rotate this around and imagine something that kind of looks like this, looking at it from the side. And all of a sudden you're thinking like, that looks a whole lot like what you just did. You just have to remember what's hiding behind it, right? I'm just showing you like the end of the iPad. There's actually a surface that's going into the screen. Got that? Okay, it's a plane this time, not a wire. So, again, if you were to imagine what happens to a positive charge, if I put a positive charge here, it's going to be like, yeah, run away. It's going to get pushed that way. If I put a positive charge on the other side, it's going to say, ah, run away. We can't really look at any other sides because, again, it's a plane. I can either be on this side or this side, and then it infinitely goes in all directions. I just can't draw an infinite plane because we would be here for a while, right? Infinite plane. Need a new page. Infinite plane. Need a new page. Infinite plane. And then you'd be like, eventually, like, that was an interesting class. Like, he just drew an infinite plane. Lecture after lecture after lecture. We don't know what we learned, but it was an infinite plane. And then the semester would end, and I'd be like, you can't leave. The plane is not complete, and never will be. Infinite plane. Okay, never mind. Need to erase this recording already. It's embarrassing. We don't need things like this floating around for consumption. So anyway, electric field. We're saying that it's this way. It either points out to the right side or out to the left side. Or rather, it's pointing out both sides. Because anywhere I drop a positive charge on the left or the right, it just gets shoved away. So, here's what we're going to do to find the electric field this time. And here is where I have literally no ability to draw this. Okay? So imagine a box. Okay? Just maybe like a cube, a box, a little cube. And we're going to essentially take the box and, whoops, we're supposed to be drawing something imaginary, so it's dotted. And we're just going to stick that box right through the plane. Okay? So it's like, there we go. We had a plane we're dealing with. And then I need a cube. I don't see any cubes of any type that's around here. Pretend this is a bottle of water that's a cube. Got that? Okay? We're taking the cube and just sticking it straight through the plane so that well, that would be disturbing if I just went and stuck it straight through there. You get the idea, right? It's stuck through the plane. So while I can't really draw that, we took a box and stuck it through the plane. It's almost like we were making biscuits. Anybody like biscuits? Biscuits? Biscuits. I'm talking like breakfast biscuits, like you'd get like in the southeastern United States a lot. Like biscuits, like fluffy, you put sausage on it, you might even put gravy on it, you might throw a slab of egg in between the two, like biscuits, okay? Except we're making square biscuits. Like we had like one of those dough cutter thingies, you have dough and you're like, chink, you stick it in the dough. I don't know what I'm talking about anymore. You get the idea. Hopefully that's enough of a description you can determine what's happening in that diagram, all right? So, if I have a box, you can imagine the right side of the box has a square on it, and there's electric field flowing through that square. The left side of the box has a square, and there's electric field flowing through that. But of course, there's also like a top of the box, and a front of the box, and a bottom of the box, and a back of the box. But electric field is just flowing past all of those sides. It's not actually flowing through those surfaces, okay? So I'm not going to write down this equation again except with like 6 terms. I'm just going to tell you that we are going to be dealing with kind of like what we had right here, right? 6 of these, 4 of them represent 4 of the sides of the box that have no flux passing through them. 2 of them represent the 2 ends of the box that the flux is actually passing through, okay? So we are going to just write something like, let's just say this. Let's write E dot dA, and we will say this is for one side, plus E dot dA for the other side. And maybe if you want to think about it, it's left and right. I'm going to draw a couple of arrows. We're going to say that this one represents that side, and this one represents that side. The other 4 sides are 0.
Are they just 0 because we're disregarding them? You said they went to 0?
They are 0 because that term, this E dot dA thing, is electric flux, which is a measure of how much field passes through. And for those other sides, it's just like going right past. It's in the same direction. It's parallel to those sides, so nothing goes through those surfaces. Okay? And on this side, Q enclosed over epsilon naught. And we're basically done. You're like, you just started this problem. I promise you, we're basically done. Watch what happens. E is just going to come out. It's constant, a set distance away from that plane. And then I've got, let's see, dA plus this other integral dA. I've got that twice. This is the area of one end, and this is the area of the other end. Keep it in mind that those ends are squares or rectangles, or technically they could be any shape you want them to be because they're about to cancel out. Okay, we'll just pretend they're squares, why not? And on this side we still have Q enclosed over epsilon naught. So, yeah, that's getting a little rough up there, isn't it? Just, all you have to do is move your head exactly with what the sheet's doing, and then there's no relative motion between you and the sheet, and it'll be fine, right? Okay, I'm going to stop trying to do that. It's kind of a challenge, though. Watch it and see if you can, like, mimic exactly what it's doing, you know? It's kind of creepy and dumb, and I'm going to stop now. So, let's see. If we have a surface charge density, we should start getting the idea of how to write the surface charge density. In this particular case, it is going to be sigma times the area enclosed, because remember this thing is equal to Q enclosed over A enclosed, and I just rearranged it. All right. If I'm dealing with a box, and if you want to think of it as a cube instead of just any old rectangular box, well then the left end of that is a square, the right end is a square, and the area that's enclosed by the box, you might imagine, is a little piece of this surface. Oh, that is like right here, like I've enclosed that much of the plane. And if I looked at it, it's a square. Yes, it's the biscuit that I cut out of the plane, okay, the square biscuit. So all the areas are exactly the same, which means I can go back down here to the bottom and write this as E times 2A. I'm just going to write area because it's an area, we understand that. And on the other side, I have sigma times the same area. Notice the areas cancel out. So it really didn't matter if it was a square or a circle or some kind of weird blob, because it turns out it just doesn't matter for the situation. And you can very quickly see that we have an answer that looks, ooh, I left out something. Do you see what I left out? I just lost a constant a couple lines back. Yeah, the epsilon just kind of went away. There we go. Let's keep that around. My apologies. This is just equal to sigma over 2 epsilon naught. Told you we were about done. You should at this point start to, like, it's hard. I get that it's hard, but you start to sort of see a trend in the way we think through the problem, and every one of them sort of works out a little bit different. There's a little twist to each one of them that's a little different. And the more you see, you start to kind of get a feel for how it's going to turn out. But the procedure is essentially the same for all of them, okay? You're going to start by thinking about which direction the electric field is going. Is there a shape that sort of fits the geometry of the problem, where at least on some surface, I'm going to have a constant value for the electric field, and maybe on some other parts of the surfaces, it's 0, okay? And then we're going to do something on the left-hand side where the area is constant, and we find a surface area. And on the other side, we're trying to figure out a way to either plug in how much charge is in this surface, or if I have a charge density, re-expressing that, seeing what cancels, and solve for E, okay? Yes, those were a lot of words. I said a lot of things there. I have 2 problems that I want to give you in a little bit, but not quite yet. We're going to end the class with those instead. Does anybody have any questions about what you see up here right now? Strange sound. Anybody? Anything? Just silence all around? Has anybody signed up for WebAssign since I've been talking? Yeah, okay. I thought there might be a couple of you out there. More are going to do that, and that's good. That's fine. Get that done. I'm going to check the numbers again later. We'll see what we're up to. Okay, so let's go over to this slide. And actually, the next one I've already crossed out because it doesn't help us at all. We don't need to talk about that. So this is the last one I'm going to talk about. And it turns out what is on this slide sort of just brings together the last 2 chapters. We talked about electric fields and conductors in the last chapter. We basically said a few different things. First of all, the charges are sort of free to move around. So if I have a conductor, the electric field is perpendicular to a conductor, but also it can't be inside a conductor, okay? We can use Gauss's law to show that at least that last one is true. Electric field is 0 inside a conductor. So here we have 3 different random shaped conductors, okay? So first of all, if we were to assume that there is no electric field inside this conductor, so we're going ahead and making this assumption, let's see what it tells us, okay? So notice they've drawn a Gaussian surface sort of just inside the edge of this conductor, okay? Meaning that when I write out E dot dA for this particular problem, like so, I know that if there's no electric field inside the surface, then there's no electric field like passing through my Gaussian surface, which means that this side is 0, which leads to this idea that the charge that I've enclosed has to be 0. Which means if there's no electric field inside the conductor, then we also know that there is no Q inside the conductor. It is all on the surface. So it's like we assumed one of the things that we know to be true, mixed it with Gauss's law, and we get the other thing that was in our list of things about conductors and electric fields. All the charge has to live on the surface if there's no electric field inside. And a quick version of Gauss's law shows that, okay? On the other hand, if we had a conductor that like had a hole cut out of the middle, and again, it looks like someone cut a biscuit out of that conductor, just like a circular hole right in the middle of it, okay? Where's the charge? We think it's all on the outside, but you might be like, hey, there's a surface like inside that hole. Maybe it goes to all the surfaces on the conductor, including the little interior surface inside that hole. Well, keep in mind, once again, we know that the electric field has to be 0 inside the conductor, which means if you draw a Gaussian surface the way they did, and there's not a good way for me to point to this, a Gaussian surface here that is inside the conductor, you can see that those little green dashes are actually in the conductor itself. Well, I know that electric field can't be passing through that Gaussian surface. It has no option, which means that, well, there can't be any charge enclosed. There's no electric field passing through the dotted line. There's no charge enclosed, which means this interior surface, there is no charge here. Instead, when I drop charge, it all goes to the outside surface, all on the outside surface of a conductor. Okay? No electric field in a conductor leads to the idea of no charge enclosed by that Gaussian surface, which tells me that some of the charge doesn't run to the interior surface. It still gets as far away from each other as possible and goes to the outer surface of a conductor with a hole cut in it. Which brings me to this third one, which after we introduce the new chapter is going to lead to one of the problems that I want you to do. I'm going to give you kind of an intermediate sort of like relatively easy, but with a new idea and a new twist that I'm going to tell you about right here, okay? Notice what they did. They took a conductor. We're going to start with a conductor that's neutral. It has no charge on it, but then they drop a charge into the little hole inside the conductor, okay? Into that empty space that's inside the conductor. And then once again, try to figure out what happens with the charge, okay? So let's think about this just a little bit. Notice the way that they've drawn the charge. For whatever reason, they've decided, hey, I've got a bunch of negative charges on the inside of that little surface now, and now a bunch of positive charges on the outside, okay? Let's see if we can figure out why they did that. Keep in mind, if I draw the Gaussian surface here where they did in the conductor, the electric field there has to be 0 because it's inside of a conductor. That means that the charge enclosed has to be 0 inside that Gaussian surface. If there is physically a charge that's here, I've got a little bit of a problem. It almost seems like a contradiction all of a sudden. I can't have any charge inside this Gaussian surface because there can't be any electric field passing through that Gaussian surface. So if there is physically a positive charge here, it has to be canceled out by some other charges. So those negatives that they've drawn literally exist, and I don't really like where they've drawn them, sort of just on that interior surface, such that it's inside my Gaussian surface, the dotted line. That negative charge is equal to a total of negative Q, so that now plus Q minus Q, there's still 0 net charge enclosed inside the Gaussian surface. Gauss's law tells me that essentially by putting physically a positive charge in the inside, it attracts a bunch of negative charge to it, just enough to cancel it out, okay? If I pull a bunch of negative charge to the inside, that means it had to come from somewhere else, and that leaves a net positive charge elsewhere. So all of these positives that they've drawn on the exterior surface, they all must add up to be positive Q, okay? Putting that positive Q in the inside drew enough electrons to it to cancel it out, and that left a deficit of electrons somewhere else. So keep in mind, the conductor started with no net charge. Putting a charge in the middle made the charges redistribute themselves to make Gauss's law work out, okay? Yeah?
So did the conductor become polarized?
You can think of it as polarized in a way. It's kind of like, I don't know, like radially polarized, like there's charge on the inside, charge on the outside. But yeah, you can think of it like that. That's the end of chapter 23. Or is this 24? I'm confused now. 23?
23.
Are you sure? 23? Okay, I believe you. We're going to come back to Gauss's law in about 15 minutes. Can you listen to me for 15 more minutes? That's a lot of people looking away again. It's like, I don't know. I don't want him to see my eyes. I don't know if I can do it. I can't do it 15 minutes. It's a long time, 15 minutes. All of you stand up. Just stand up. You can do it. Just stand up. Oh, you're just going to leave. I say stand up. He's like, I'm not here. That's fine. Okay, I don't like this.
There's something intimidating when you all stand up, because now all of a sudden, even though I'm standing on a step, I feel short. It's like, and now if I like walk down here, I'm like, so many of you are bigger than I am. Now I just want to run back up here again. So before you sit down, we're going to try something. How many of you are sleepy right now, even though you stood up? Yeah, a lot of you are sleepy. I heard that laughter makes you wake up, even if you fake it. So in other words, right now, all of you just fake like you're laughing. And if you're, even the faking will turn real if you fake it hard enough. Are you ready? No? Like we're just like belly laugh, just roll like this is the most hilarious thing ever. And by the time we sit back down, we're all going to be relatively awake, enough to listen for like 12 minutes is what I'll have left at that point. So are you ready? Don't make me do this by myself. You laughed there, but that was almost genuine. Ready? We're going to laugh loudly and fakely. Okay? And go. Help me. That was sad. So I want you to remember this, and we're going to do it again, and we're going to fake better next time. No? Sit down. It helps a little bit. Who's still sleepy? Okay, yeah, that's fine. I know. I'm chronically sleepy. My wife thinks I might have narcolepsy, but like of a type where I don't just like pass out all of a sudden. It's just more of a chronic tiredness in that if you just give me a minute, I'll pass out just like at any moment. So I don't know. I should be tested. Sounds like I'd get to do a sleep study. That sounds like the best, right? Like the doctor says, come in and go to sleep. Thank you. That sounds fantastic. You know, I'm happy to sleep anytime, anywhere someone wants me to. So here we go. This is the new chapter, chapter 24. We're going to talk for just a few minutes about this. I just want to get you started with the concepts, and then I'm going to have you do 1 or 2 Gauss's law problems for me, okay? So, if you think back to Physics 220, you're like, Physics 220, or whatever equivalent class you had, the first physics class with calculus, okay? Things probably started out with like motion. You dealt with things that were moving around, and then you talked about forces and determined like, hey, forces are making these things move. And once you got done with that, you might have started talking about energy, things like potential energy and kinetic energy, conservation of energy, and it was almost like a new way to do the exact same things. In fact, you probably discovered that like with things like projectiles, you were like, oh, I can use all these motion equations, or I can just say, hey, it has this much potential energy and this much kinetic energy, and I can quickly get to the answer a lot easier. And maybe some of you thought like, this is a lot better. Why did they teach me all that other stuff and make me do it that way? Okay? We're doing a similar thing now. We talked about forces. We talked about the electric field. Those two things are sort of tied up together as like one way to describe how some forces, some charges impact other charges. It was a way to describe that like positive charges will repel each other. Negative charges will repel each other. A positive and a negative will attract each other. And that's essentially what we spent the last 2 chapters analyzing in a very intensively mathematical way that kind of hurt a little bit. Agreed? And now you're going to have to do a lot of homework and practice a lot and go back and try to sort all that out and ask each other questions, ask me a lot of questions, send me a lot of emails. I just hit, I have a button, it just replies LOL and archives it. Like, I want to develop that just to mess with everybody. Like, lol and archive. I think that'd be fantastic. I could get in a lot of trouble that way, I think. Especially if it's like department chair, lol and archive. Someone else, lol and archive. But no, I'm not going to do that. Ask questions as you delve into those 2 chapters. We're going to start thinking about a lot of the exact same things from the standpoint of energy. So you can see right at the top there, electric potential energy, okay? So here's the thing you need to remember. First of all, this electric force, you might remember the idea of conservative forces. Conservative forces, like, they don't waste energy. In other words, when they do their work, they don't just throw energy away. So we have things like gravity, that's like gravity can have a potential energy. So like the pencil right now has gravitational potential energy. If I drop it, well, it loses its gravitational potential energy. But I can just pick it right back up again and get that energy back. It's not like it's just like gone forever and I can't get it back. On the other hand, something like friction, right? It's like, well, if I shove the iPad that way, it stopped because of friction doing work and essentially taking away the energy that I gave it. I gave it some energy. Friction said, I don't care about your energy. I'm going to stop this thing, suck all the energy out of it, and throw it away, and you can't have it again. Friction is non-conservative. It doesn't keep the energy around. If it were conservative, like gravity is, you might be like, push the thing this way, and then friction says, yeah, you can have it back. And that'd be a creepy world to live in, right? It doesn't work that way. How come it doesn't bother you when gravity does it? Gravity threw it back to me. Why doesn't that bother us, right? I threw it up in the air. I gave it some energy. Gravity said, I'm going to stop it. I'm going to stop it. I'm going to take away its energy. And then, oh, here, you can have the energy back. I'm going to push it back to you. It's a conservative force. It didn't waste any of the energy. Friction doesn't work that way. Boy, I wish I had a string right now attached to this so I could just be like, whoop, and pull it back. Friction just takes the energy and says, it's done. I did not conserve it. On the other hand, the electric force is a conservative force. It doesn't waste energy. If it does some work and takes energy away from something, it stores it as potential energy and can put it back into the charge. So conservative forces have potential energy associated with them, okay? So I have this force that is the electric force, and it's going to be connected to electric potential energy. And maybe you used U for potential energy, maybe you used PE, whatever, it's all kind of the same. The electric force is associated with the electric potential energy. So if I were looking at the change, let's see, do I want to do it that way? I don't know. Do I? Yeah, let's do that. The change in potential energy, meaning the difference in potential energy, say, between two different points. It's equal to the negative of the work. This is like an equation you should have seen last semester. This is just in general for any potential energy. And we can use that equation and get some new stuff dealing with the electric force and the electric potential energy relatively quickly. Does anybody remember anything about work and what equation we have for it?
Force times distance.
It's basically a force times a distance. There's more complicated forms of that, but essentially it's force times distance. So in this particular case, I'm going to write it as an electric force, since that's the one that we're worried about, times some distance over which that force acts. So if I want to know how much work is being done by an electric force, well, the force is being applied to a charge, and that's happening as the charge moves a certain distance. Notice it's also equal to how much the potential energy of that charge changes as it goes from one point to another. And I can rewrite this one more time because we have an equation for the electric force. We can connect it back to the electric field. It's equal to QE. So we have that equation for both work and change in electric potential energy. So this is equal to work and the change in potential energy. So what do we mean by electric potential energy? In a way, it's not all that different from gravity. Okay? If I take a mass put it in some gravity, right? Right now, it has gravitational potential energy because it's feeling the force of gravity and it could fall, okay? If it starts at this point and gets pulled by the gravitational force downward, you might imagine as it's going lower and lower, well, that force is doing positive work on the mass and the amount of potential energy is decreasing until we get to the floor and there's no potential energy left because it can't fall any further, okay? We have a similar sort of thing in an electric field. So again, this electric field concept, think of it like gravity. Like gravity is in existence in this region of space, and if I put a mass in gravity, it gets moved by the gravity. The electric field exists in this region of space, and if I put a positive charge in that electric field, it feels a force and gets moved, all right? So you can almost think of this region here, and I hate that this is so close together. In fact, let's draw it again ourselves. Let's imagine that there is an electric field that points like this, and it's being created because there are a bunch of positive charges up here, and there are a bunch of negative charges down here, creating this electric field in between that region of space. So that if I take a positive charge and put it all the way at the top, it can't go any higher in the electric field, it's going to have the most potential energy it can have. So here it has high electric potential energy. And of course, it's going to feel a force that repels it from those positive charges, and it pushes it in the same direction as the electric field. It's almost like it's falling to relate it back to gravity again. But just keep in mind, I only oriented it like this to make it kind of like gravity, so that down was the direction it wants to go. I could tilt this at an angle, and then my charge would sort of fall along the electric field this way. I could make it go all the way upside down, and now my charge would fall up in the direction of the electric field. So in a way, like, gravity is a thing that exists. We know how it works, but we don't have a lot of control over it. If I have something that's charged and an electric field is something I can control, I can sort of make things move whatever direction I want them to. So it's like this powerful, fake sort of gravity, right? That I can make charges move the direction I want. So that means by the time the charge gets all the way down here, well, now it doesn't really have any potential energy left. We could say it has low electric potential energy. So as the positive charge follows the electric field, its amount of potential energy is dropping. Just like when the mass follows the gravity, right, and goes with the gravity, its amount of potential energy is dropping. Do you see the comparison between those two? Maybe a little bit, okay? Here, a positive charge falls in the direction of the electric field, has lots of potential energy when it's near other positive charges, and low potential energy when it sort of gets to the end of the line, when it's near the negative charges. Keep in mind, mass is just mass, right? Mass, there we go. Mass like attracts other mass. When I'm dealing with charges, I have positive and negative charges, which means I could do something like this. I could put a negative charge in here. If I put a negative charge here at the bottom, what can you say about its potential energy when it's at this location? It has high potential energy, right? Because it really wants to go this way. It can fall in this direction against the electric field. So we would say here a negative charge has high potential energy, electric potential energy. And once it gets done falling and reaches the other side where there's nowhere else left to go, then we would say it has low electric potential energy. So this whole thing is analogous to gravity, but in a lot of different ways. It's like more powerful, it's more versatile. We
can do a whole lot more with it. And we have a lot more control over it with the technology that we have. Maybe one of these days we'll have, you know, artificial gravity where we can control it and just be like, you know, I think all of us are feeling a little heavy today. And we just like turn the knob down and we start to float out of our seats. That'd be kind of fun. Kind of scary, kind of fun. Maybe one of these days in the Star Trek universe that I'd very much like to live within. Sigh. One of these centuries, one of these centuries. First, I need to live for a long time. So we need to reach the singularity, and then I need to plug my consciousness into a computer, and I don't know, things have turned sideways now. So it is 4:23. I'm not going to introduce a new topic. Instead, I'm going to draw a couple of pictures on a new slide for you. Hold on, I'm just thinking here. There's a lot of whiteboard space up here. As many of you as want to. Like, it would be easier for me to see your work and be like, what are you doing there? And like kind of point out what's going on and for you to ask questions. If you want to bring a group of 3 or 4 people and crowd around a little area of the whiteboard and work these problems, I think it's good for you and good for me and good for your awakeness, sort of in general, if you're not just sitting there being like, I don't know how to do this problem. I don't know how to do this problem. Instead, you're like up here kind of fighting with it with someone else, okay? So either find a spot on the whiteboard or mill about and find a group of 3 or 4 people and try these problems, okay? I'm gonna put one up here. All right, how is everybody doing on this Physics Friday? It is Physics Friday, right? Physics Friday, Thursday? Something kind of like that, yeah. Yeah, where is everybody today? What happened? Strange. Just like a week ago, people were clamoring at the door, trying to find a spot. It's curious. Yeah? It's disappointing. Now I'm sad. I don't know if I can do this now. Look at all these people missing over there, like a whole slew. Yeah. We should, shouldn't we?
That'd be very nice for us.
Yeah.
And for them.
We should have like extra class because they're not here, like to punish them. Or does that punish you all? I'm not sure which.
And you.
And me? Yeah.
Because you have to be there too.
Yeah, it punishes all of us. We can't do that.
Yeah.
Ah. I like that. I should teach things today that all of us agree to never share with them. And then it is a question on the first exam. Yes. That's pretty good. Yeah. Like the answer for 30% of the test is B. The last third of the test is B. And now you know that. No. That'd be pretty fantastic, though. Boy, that'd make grading easy on that part of the exam. I couldn't complain too much about that. You know, I'd like to.
Well, you really don't have to.
But I really don't have to.
The answer could just be B for like math questions.
Oh, yeah. It's like,
B for math questions. Oh. So they think it's like the answer is like 60, but it's B. Okay. Huh. Things to think about. We should see who shows up on Tuesday and following. Now maybe those of you who are here, you're thinking like, dang it, I was thinking about skipping out. And now you're wondering what might happen. Somebody just got revealed. I saw that. Slapping someone across the aisle. That's wrong. All right, so let's see. Today, I have tried 2 experiments today trying to record the lecture another way and failed both times. Mostly because I ran out of storage on my iPhone both times in 2 other classes, which was depressing. I wanted to record 4K video because I was like, ooh, it'll look fantastic on YouTube, right? And it was like, that's going to be 15 gigabytes, and I didn't have that much room. So I was like, fine, we'll try 1080p. And it's like, still ran out of space. So I'm stuck with the system here, which is 720p, which, you know, it looked okay, but it could look better. You know, you kind of want to be able to see everything that's up there in ultra high definition, but I don't know. We'll have to see. So I'm going to do this for now, and we'll go from there.
I'll experiment some more. I'm not guaranteeing, once again, that I'm going to record this every time. People who aren't here, you might not ever get this lecture. Maybe they were thinking, I'll watch it later. Maybe you will, maybe you won't. We'll see. Maybe I'll just leave gaps in the middle. I'll just hit pause every now and then. They just kind of stop. So we were talking about electric potential energy. Electric potential energy. Keep in mind all three of those words together mean something different than just electric potential. Notice on the next slide, like the word energy drops off. Don't think that like we're just going to start using shorthand. It's like, forget energy. We know it's energy. These are actually two different things. And I hate the fact that two very different things have almost the same exact terminology. It's a bit of a problem. So let's go back and first describe again what electric potential energy is, and then I'm going to contrast that with the next slide and what electric potential is. So we've got some equations up here that will tell us how much potential energy a given charge has, and it's all dependent on where that charge is located inside an electric field. Keep in mind, if I take a charge and just put it somewhere where there's not an electric field, it has no potential energy because it has no motivation to move somewhere else. Much like if I take a piece of matter and just put it in deep space somewhere where there's no gravity, well, it has no gravitational potential energy because there's no force that's pulling on it in any given direction, okay? It can't fall. In this particular case, if we put the charge in an electric field, it sort of wants to fall in the direction of the electric field. It feels a force that way. Keep in mind, if I use a negative charge instead, it will feel a force the opposite direction. It sort of wants to fall against the electric field. We say that when there is the possibility for that charge to move, to feel a force and go somewhere else, it has electric potential energy. Much like a mass, if it wants to feel gravity and go somewhere else, has gravitational potential energy. Okay? Do you have the idea of what this potential energy means? Do you have questions? Do you get it? Yes? Yes. Okay? Let me point out something on this diagram over here at the right. I feel like if we keep zooming in far enough, we're going to like see a little creature hiding in here somewhere, you know. It's like, hi. But, you know, there's nothing there. Just forget that. Okay? Notice these words, potential energy, are pointing to the charge itself. In both cases, and this is important, like they took this line, they drew it literally into the charge, and that was no accident. Because it is the charge that has potential energy. It has a certain amount of energy because it exists in this electric field. Okay? When we talked about masses and gravitational potential energy, it is the piece of mass that has gravitational potential energy because it will fall somewhere, all right? This is different from, next slide, potential. Leaving the word energy off. Let me start by looking at this diagram over here. Notice the arrow here is connected to these words, and it's kind of just pointing to this point right there next to the charge. Again, when they drew these diagrams, this was no accident. The energy is something that the charge possesses. The potential is something about a point in space where there isn't necessarily a charge at all. It's saying that this location, right there, next to that solid plate, has low potential. On the other hand, over here, this little location right here up against this plate is a location that has high potential, all right? If we go back and look at the definition, I literally wrote out, it's like the potential, quotes, of a point in space. How much possibility that location possesses, okay? Let me explain a little bit more by, well, again, relating it back to gravity. So if we were dealing with gravity, notice they put two different size rocks up at the top. We could assume that those probably have different mass. Well, if they are a certain position off ground, we would say that those two pieces of mass both have gravitational potential energy, but a different amount because they have different amounts of mass. You might remember that gravitational potential energy, we could write that as, if you don't mind, can I just write it as PE? Sometimes U is used, but PE, gravitational, is equal to M times G times H, right? So how much gravitational potential energy a piece of mass has is not just based on where it's located above the ground, but also based on how much mass it has, okay? On the other hand, if I were to just say, remove these rocks, yeah, that didn't really remove them, that just colored them, right? And it's like, yeah, I have green rocks now, fantastic. Pretend they're just not even there. How can we do this? I don't know what's happening at this point. They're not there anymore, okay? Those locations where the masses were, they're still in existence there. There's still points in space there that exist this height above the ground. We might say that these locations have potential. They have possibilities. They have options. Because if I put a mass in those locations, those masses will now possess potential energy. It's a subtle difference. Do you hear the way I'm describing those two things? The locations where nothing is located, these locations at height h above the ground, have potential. Literally, they have gravitational potential because if I put a piece of mass there, it will possess potential energy, okay? So in terms of the equations, what we might do is write something like this. Boy, I really hate this, but V is what we use for potential. And this is part of the reason why I switched from using U here, because writing a U and a V, trouble, right? So potential energy is mgh. We might say that the potential of those points in space is just G times H. If we were to get rid of the mass, like don't put a piece of mass there, and let's just talk about how much opportunity those points have. Well, they have some potential because there is a height above ground level, and it exists inside of a gravitational acceleration or a gravitational field, all right? So let's relate this back over to electricity and magnetism and all this sort of stuff, and let me make sure I write down the right things. Question?
So V equals GH with no rocks, when rocks are gone?
If the rocks are gone, those points at that height still have potential. Okay, so we might call this gravitational potential. And this up here is gravitational potential energy. Okay, now over in the electricity side of things, right? Notice we again have this little setup where we can create an electric field in between all these positives and negatives that are on these plates. So there's an electric field that's pointing that way because a positive charge would be pushed from the positive side over toward the negative side. And notice this time they don't have masses. They've decided to put two different charges here, right? One is just charge Q, and one is charge 2Q. Kind of like the masses where I had a mass and then a bigger mass. Now we're dealing with charges. We put them in here, and when they are in this location, we've already learned that they have potential energy, electric potential energy. And we had an equation over on this previous slide, QED, okay? So potential energy, electrical, and I'm going to write this as a magnitude, is equal to Q times E times D. Okay? If I take the charges out, that hasn't changed that region of space. There's still an electric field here, and that point in space is still a point that has a lot of opportunity, a lot of possibility, a lot of potential. Because I know that if I put a charge there, it will possess potential energy because it wants to be pushed this direction. So notice the way these equations are working out. Here I said, okay, remove the mass, and then I can say that this location above the ground inside of gravity has potential. Look at this equation. I can say that if I take out the charge, so let's do that down here, V sub E just equals E times D. These look an awful lot alike, right? Notice there's a certain location, okay? It's a certain distance away from the farthest place it can move to, and it's inside an electric field. Here I had a gravitational field. Here I have an electric field. Those points in space have potential. So the difference is points. Where nothing is has potential. Charges at those points have potential energy. Okay? Can I say that again? Points in space have potential. Charges placed at those particular points will possess potential energy. Okay? So we could go over to this diagram on the left. Not the left, that's the right. Yeah, I've got problems. Apparently it's very much Friday, Thursday. Ugh. We can look at this diagram and like completely get rid of these charges. And we can analyze this setup and say that over on the left-hand side of this region, we could say over on this area, in this region of space, there is high potential, okay? And that amount of potential is going to be less and less and less and less and less as I go across here until I get over on the other side, and we would say that regions of space over here have low potential, okay? The amount of energy a charge has depends on whether I put it into a higher potential area or a lower potential area, okay? Just like, well, the iPad can fall to the floor, right? This region has higher potential than regions right next to the floor. If I put the iPad here, it's going to have higher potential energy. And if I put it in a region of lower potential, it'll have lower potential energy, okay? This is a way, kind of like we did with electric field and force. We went from force, talking about like this charge exerts a force on another charge, and then we sort of like abstracted away from that a little bit and just said that there is an electric field here such that if I put a charge there, it'll feel a force. We're doing almost the exact same thing here, saying this region of space has some properties, it has potential. If I put a charge there, it's going to have energy, okay? These things are all analogous, they all sort of fit together, but they are hard to grasp the first time through. Mostly because this is a lot of stuff that we can't see and touch and play with, and it's just conceptual, okay? I'm hoping in your labs, when you get to play with some of this stuff, that some of it kind of hits home a little bit more, okay? So electric potential energy. Let me see, I have some equations here to give you. Okay, so this one, first of all, the electric potential is equal to the potential energy divided by the charge. And if you think about it, that's essentially what I did when I moved from here down to there. I divided the charge out, and that gave me the potential. We could also write this as U divided by Q if you'd prefer to use that terminology instead. Also, the unit for potential is the volt. The unit for the potential is the volt. And it turns out that it is equal to 1 joule per coulomb. 1 joule per coulomb. And also, beautifully, this is the part you should like. It is a scalar. Yeah, at least one person understands the significance of that being a scalar. Scalar, yay! You don't have to deal with vector addition when you're having multiple things to deal with. So this is supposed to be the easier way to do similar problems. When I'm dealing with energy and potential, it's a scalar. I can just add and subtract things without having to worry about any direction information. So let's switch over to the next slide. A few points I should make. First of all, typically when we're doing problems with potential,
we want to focus on a difference in potential between two different points. A difference in potential between two different points. So I could write that something like this. Delta V, a difference in potential, is equal to the potential at point B minus the potential at point A. Or if you wanted to use that equation we had just a moment ago, we could say that this is the potential energy at point B minus the potential energy of point A divided by whatever charge is at those locations. So you see some of these equations starting to fit together now. So since typically we're dealing with a potential difference, if we want to know, like, I don't care how much the difference is between here and here, I want to know the potential at this point, just one of them. The only way for me to get this is to know the potential at one of those 2 points. And there is a way that we commonly do this. We pick a reference point, and this reference point is known as ground, which is perhaps something you've heard of before. When we're dealing with something known as ground, this is a location where the potential, the electrical potential, is equal to 0. So that means if I know the difference in potential, say, between this point and ground is 0, well then the amount of potential at this point is equal to the potential difference. You can see that in this equation, okay? And by the way, ground, we're going to do circuits and stuff later on. Typically, this thing, ground, is literally the ground, meaning Earth. It turns out that the Earth is basically a sort of an infinite reservoir of electrons, of charge, and I can send it a few more charges or I can take a few out of it, and it sort of doesn't care so much. It's negligible to something the size of the Earth. It allows us to have a region of space where there really is no potential, okay? Sometimes also, or we'll say alternatively, we will use R equals infinity, meaning far, far away from any other charges. As a location where V is equal to 0. And I think that sort of makes sense because it's just like with the mass. If I put the mass way out in space somewhere, it doesn't feel any gravity, so it has no potential energy from gravity standpoint. The same idea works with charges as well. And then one more equation. You can see here at the bottom it says the potential difference tells us something about how much energy a charge can gain or lose, or how much work it can do. And we can get back to this idea just by simply rearranging some of our equations. The change in potential energy is equal to Q times the potential difference, or Q times VB minus VA. So reading through this equation, if I have a charge Q, and then there are 2 points where I know the potential. So maybe I know the potential here, and I know the potential here, okay? If I take the charge and it moves from one point to the other, and I know the value of the charge and what the difference is in potential between those 2 points, this will tell me how much its potential energy increases or decreases as it moves between those 2 points, okay? So what are we going to do with all of this? First of all, a slide just with clarification. Notice over on the right, U is electric potential energy, and it is a type of energy which means its unit is joules, just like energies you had before. Other types of potential energy, kinetic energy, all that type of stuff, units of joules. Different from that is this thing that we're calling electric potential. For it, we use V, which is also its unit is in volts. Sometimes we get even a little more lazy with that and just say potential all by itself. So if you hear just the term potential, we're talking about the exact same thing. We're still talking about V, and it's measured in volts. So these two things at the bottom are exactly the same
but they are different than potential energy, okay? So we've got potential and we've got potential energy, two different concepts. Just in case you care a little bit, potential differences that exist kind of throughout the world in different things to give you a feeling for what a volt is and kind of where those things are experienced. A flashlight battery is built such that there is a difference of potential between one end of the battery and the other end of the battery, which is typically maybe about 1.5 volts, give or take a little bit more. You can see as you move up from that, an outlet in your house is typically about 110 volts of potential difference. And keep in mind, potential difference combined with charge starts telling you about how much energy is there, how much potential energy. And of course, as these go up, these are seemingly more energetic, right? Until we get all the way up to the top, thundercloud to ground, which results in lightning. Lightning happens because there's charge that's moving from a very high potential to a very low potential, and you can see the difference in potential there is 10 to the 8th volts, which results in quite the current flow or charge flow from clouds to ground, which is kind of sad, scary, and exciting, and scary. But a little exciting to watch, but scary, okay? So let me ask you a few different questions here related to potential and potential energy. I'll give you a moment to read it, and then we will talk. Hey, things aren't blowing in the breeze today. Should I do this? Did you kind of enjoy that today? The other day, is it kind of soothing? Could I please stop? I'm trying to read. Okay, I'll stop. I wonder where this phone goes. Can I call anything on this phone? Is that like a phone? Or is it like the scary emergency phone that only like dials one number if I pick it up? You should call yourself. See if it works. You might just pick it up and they're like, police. You know, I don't know. Why is there a phone? I don't need a phone. Do you need a phone in here? I don't think so. What's the answer? Any thoughts? 1, 2, 3, 4, or 5. Vote. Vote if you think you know the answer. You're like, we haven't even been reading. We're thinking about this stupid phone. Who says 1? Who says 2? Who says 3? Who says 4? Who says 2? I caught some of you. Who says 5? They feel the same magnitude force, but opposite direction. I would agree with that. Number 3 is meant to trick you just a little bit. But keep in mind, force is equal to, well, Q times E. A proton and an electron have the same Q, and they're in the same E. So they're going to feel the exact same force, but they're going to want to go opposite directions in the electric field. So let's quickly draw that in. The proton is going to be pushed this way, and the electron is going to be pushed that way. So in a way, that's a little bit of a review question from last chapter. What about this one? One, 2, 3, 4, 5, 6, 7. We ran out of questions. I don't know what else. So they experience the same force, but keep in mind an electron and a proton have very different masses, right? A proton is much heavier, which means that the lighter thing is going to have more acceleration. So that would be the electron in this case. Will experience more acceleration. Let's see.